Welcome to this maths video brought to you by Up Vision Concept Academy. This video is tailored towards those that are writing WAEC and the JAM exams. In this video, we'll be looking at the geometric progression, GP. And at the end of this lesson, we'll understand the concept of geometric progression, identify the common ratio and the general sum of a GP, apply formulas for the nth term and the sum of them in a geometric sequence, then solve real-world examples. So let's dive in. So a geometric progression is a sequence of numbers where each term is obtained by the process of dividing a term by the preceding term to get a constant number. Example of a geometric progression is 2, 4, 8, 16, 32, 64, 128, etc. Another example of a geometric progression is 81, 27, 9, 3, 1, and so on. Now, in these two examples of a sequence, the first thing you identify is that this sequence occupies a position. So this is the first term. This is the second term. This is the third term. This is the fourth term, the fifth, the sixth, the seventh, and nth. You understand? So the positions of where this number is occupying is known as the term. So they are positions. And there's also what we call the first term. The first term is A, the number that starts the sequence. Understand? So for this particular first sequence, A, the first term is 2. And for this one, the first term is 81. So the common difference, R, is defined as the constant number that comes from the division of a particular number by its preceding number. So if I divide 4 by 2, I get 2. If I divide 8 by 4, because 4 precedes 8, I get 2. If I divide 16 by 8, I get 2, and so on. If you see the division continuously like this, you see that it's a constant number that comes out. That constant number is known as the common ratio. Same thing applies here. If I divide 27 by 8, I get 1/3. If I divide 9 by 27, I get 1/3. If I divide 3 by 9, I get 1/3. If I divide 1 by 3, I get 1/3. So 3 here is the common ratio. So you see how division goes. You don't just divide anyhow because you get like this. You don't have to divide this like no. You divide, from right to the left. So you are dividing a number by its preceding term. This one does not have common ratio this way because there's nothing preceding it. So this one has a preceding number. If I divide this by preceding number, I get a common ratio. So from what I have already described here, I can see I have 3 parameters defined. A, first term. Then R is common ratio. And N is the nth term. That nth term is the position of that term. It could also mean how many of it. Understand? This one I've listed here now till 7. These are 7. There are 7 terms already in this GP. So what determines a GP is the common ratio. The common ratio, the way it is gotten by dividing a term by its preceding term. And you see that division, if it's done in that order, you see that number is a constant number. Now, all these are related when we want to look for the nth term. To find the nth term, the nth term of a GP is given as Tn, where Tn is the nth term, is equals to AR raised to the power n minus 1. This is the times here. So Tn, the nth term, is given as A times R raised to the power n minus 1. You know what A is already from this differentiation. R common ratio, n the number of terms. So we'll quickly just apply this what we just defined in a practical question. It says find the sixth term. Find the sixth term. An example, please. Example. Find the sixth term of the GP. Okay, so the GP is given as 3, 6, 12, 24, yada yada yada. Okay, so that's the GP. So the system, I have 1, 2, 3, 4. So the system is hidden. So how do I do that? I just say T6, which is system, is A. A is what? A is 3 times R is what? When you divide 6 by 3, you get 3. And then N is the sixth minus 1. This minus 1 is always constant. So I come here, T6 is equals to 3 times. Do this math first before you multiply by this. So 6 minus 1 is 5. So 3 raised to the power 5. Sorry, R is not 3, R is 2. Please, R is 2. R is 2, please. And to do you well, if you define, quickly bring out the parameters and substitute. So this parameter here, A is 3, common ratio R is 2, and the N is equals to 6. That's what we have here. Okay, so 2 raised to the power 5 is 32. So T6 is equals to 3 times 32. And the final answer here is 96. It means that the sixth term of this GP is 96. After this one, you will see 96, which is the answer. Okay, so we will progress again, and we will look at another definition. We are going to be considering the sum of terms in a GP. There's a formula for it. The sum of terms in a GP. The sum of terms in a GP. Okay, so I'm going to write it on the board. Sum of terms. Sum of terms in a GP. Okay, so the sum of terms in a GP is given as Sn is equals to A, open bracket, 1 minus R raised to the power n over 1 minus R. But this is if R is not equals to 0, not equals to 1. But in cases where if R is greater than 1, the formula can be written as this: A, open bracket, R raised to the power n minus 1, close bracket, R minus 1. So this is for R greater than 1. That's the formula. So let's quickly apply this example. So sum of terms in the GP. Please note the definition. A is first term, R is common ratio, and N is the number of terms that we're considering. So we say we should find the sum of the first 5 terms of the GP. So the GP is given as this: 5, then 10, then 20, and so on. And so on. The manual way of doing this is to write out this one. You know, after 5 is 10, after 10 is 20. Then the next one is supposed to be 40. Why? Because if I divide this by 5, I get 2. So I'm multiplying by 2, right? So the next one, if I multiply by 2, let me just put it there. 40, multiply by 2 again, 80. That is 1, 2, 3, 4, 5. I'll now add all this one together. I'll add it together. But we're not going to be going through that route because it's the manual route. Sometimes these first 5 terms, they can tell you to find the sum of the first 11 terms. And you know you're writing JAMB. Time is of the Excel. You need to be fast. So find the sum of the first 5 terms of the GP. So first of all, we take our number of the terms. We use this formula. Let's use this formula. Okay, so why? Because R is greater than 1. R is 2. So for this formula, A is defined as 5. R common ratio is 2. And N is what? First 5 terms, 5. Okay, so if I have sum of first 5 terms, S5 is equals to A R raised to power N minus 1 all over R minus 1. So where I see A, I put 5 outside. R is 2 raised to power 5 minus 1 all over R here is 2 again, minus 1. That's sum of the first 5 terms of this GP. So I continue. So I saw what's in the bracket first. Sum of the first 5 terms is equals to 5 is outside. 2 raised to power 5 is 32 minus 1 all over 2 minus 1 is 1. Sum of the first 5 terms is equals to 5 times 32 minus 1 is 31 all over 1. And this will now give me 155. 155. So this is sum of the first 5 terms. So if I add 5 to 10, 15, 15 plus 20, 35, 35 plus 40 plus 80, everything will give you 155. Okay, so that's the answer. So we're going to be looking at sum to infinity of a GP. Sum to infinity of a GP. So let me quickly take this one off. Okay, so sum to infinity of a GP. Remember, GP is geometric progression. So the formula is given as S infinity is equals to A over 1 minus R. Simply, once you see, say, find the sum to infinity of a GP. This is the formula I'm going to use. Example. If I have this question, they say find the sum to infinity of the GP. What the GP? GP is 8, 4, 2, 1, yada, yada, yada. So the solution is to use this formula. S to infinity is equals to A over 1 minus R. What is A? A is 8 and R is what? What's R? 4 divided by 8 is half. 1 over 2. 1 over 2. So S to infinity is equals to 8 minus 1. Sorry, 8 over 1 minus 1 over 2. Which is simply saying 8 over 1 over 2. And this is division. So 8 divided by 1 over 2 is the same thing as saying 8 times 2, which is what? 16. The answer. So that is sum to infinity of that GP. So you just apply that formula and you get your answer. So we're going to be applying it to. Okay, we're quickly going to just solve some practical questions. Let me give us the time to solve some practical questions. Okay. So if we're told to find another example, say find the 8th term of the GP 2, 6, 18, and so on. From here, the common ratio is 3. Common ratio there is 3, right? So find the 8th term. Easy. Just T8 is equals to AR n minus 1, where A is equals to 2, R is equals to 6 divided by 2 is 3, and 18 divided by 6 is 3, and n is equals to 8. Just put it there. T8 is equals to A is 2, R is 3, dot 3. This dot is times. Always say into your mind when you are putting dot. Say it to your mind that it's times so that you can know that it's times. Then n is what? 8 minus 1. Okay, so T8 is equals to 2 times 3 raised to the power 7. And 3 raised to the power 7 is what? 2187. T8 is equals to 2 times 2187. And finally, T8 is equals to 4374. That's the answer. That's the answer. So the 8th term of the geometric progression is 4374. Okay, so we have another example I'll quickly put on the board. It says sum of the first 7 term of the GP is, find the sum of the first 7 terms of the GP. The sequence is 4, 12, 36, and so on and so forth. So sum of terms, first of all, what's the common ratio? That's what we're interested in. If I divide 12 by 4, I get 3. If I divide 36 by 12, I still get 3. So R is equals to 3. Okay, let me start with A. We're going to start with A. A is what? A is equals to 4, R is equals to 3, and N is equals to what? 7. We're applying the sum of the first 7 term, which is A, open bracket, not open bracket, A, R raised to the power N minus 1 over R minus 1. Okay, so S7 is equals to what's A? 4. Then R is what? R is 3, N is 7, dots, or let me close bracket. There's 7 minus 1 all over. R again is what? 3 minus 1. Okay, so S7 is equals to, when you raise this 4 is outside, though, please, times. Then 3 raised to the power 7 is what? 2187 minus 1. 3 minus 1 is 2. 2 here 1, 2 here 2. So this is S7 is equals to 2187 minus 1. Okay, let me just do the minus quickly. Let me do the minus quickly, or let me come up here so we can see properly. So we're done with this side, so we'll come up here. So S7 is equals to 2 times 2186. Why? Because this sum has been done. So that's 2186. Then the final answer will be S7 is equals to 4372. Answer. Okay. So there's something I want to introduce us to quickly, and that is the application of geometric progression when we are looking at depreciation of assets. So let me just do one particular application. How is it applied in the real world? How is it applied in the real world? Okay, so let me just put it there as applications. Applications of geometric progressions. Okay, so first of all, let's look at depreciation of assets. Depreciation of assets. Depreciation of an asset. So if a car is bought for, let's say, 1 million naira. Let me use smaller figure. But you know it's not the same, it's not true. 1 million naira for car. And depreciates at 10% per year. The value after n years is, okay, now if you look at this thing here now that we're saying, depreciation is like, you know, every year there's a value that's a percentage that is taking off that thing. You understand? It's taking off that thing. So if the first year is 1 million, you understand? If it depreciates by 10%, the next year will be 9 million. Sorry, 900,000. Depreciation is going down now, 900,000. Why? Because 10% is taking off. You understand? 10% is taking off. Then, and so on and so forth. You understand? Let me just stop here, because now the common ratio now with this one now is what? This over this, which will give me 0.9. 0.9. That's the common ratio. You understand? So if you want to get the depreciation, if the car is bought for this amount and it depreciated by 10% every year, so every year 10%, that means the common ratio is now 0.9. The value after n years is, you know, after nth term, the value after n years, that's the, what is the value on that nth term, So you know the formula now, Tn is equals to A R raised to power n minus 1. So the value, the nth term, the value at the nth year is the 1 million, times the common ratio 0.9 raised to power n. That would be the depreciation of that at the nth year. So that is just like a practical example of what is being used after n years. Okay, so population growth. Another way we can apply it, let me just put it on the board. Population growth. Okay, population growth. Okay, so this is an application. So if a bacteria colony doubles every hour. You see where the common ratio is coming up? Every hour it doubles. Starting with 100 bacteria, the population after n hours is, okay, now this is another way again. The first term is 100. If doubling every hour is the common ratio, so at the nth hour, A R raised to power n minus 1. Sorry, at the nth hour, this is n minus 1. At the nth hour, 100 times what's the doubles is 2. R is 2. It doubles. R is, because it's like this: 100, 200, 400. It's just doubling. So the R is 2. Then this power n. So the population after n hours is this. So we have actually gone through this topic. we have reviewed the nth term formula, sum of the GP, and application. Please go through, solve real-world problems, and also try and check past questions to see how this topic is coined. So we'll stop here for today, and I hope this video has been informative for you. I'd like to thank you for viewing. Kindly subscribe if you are new to the channel, and like our content to enable people to see more of what we are doing. Thank you for viewing.